Now for a theorem. If the series a sub n, the sum of all of these terms, is convergent, then the limit as n goes to infinity of a sub n is going to equal to 0. That just is going to be the truth. So we can come up a test for divergence. We can say, well, if we take the limit of a sub n and it doesn't equal 0, then we can say definitely the series is divergent. And look here, this is really important. The converse of this is not true, okay? If n goes to infinity of a sub n, if we find that the limit goes to 0, we cannot say that it's going to converge. That doesn't tell us anything. It doesn't tell us that it converges. It doesn't tell us that it diverges. The only thing we can say for sure is that we know if it's going to converge that this will equal to 0, and we know if it doesn't equal 0, then it's divergent. That's the only thing we can say for sure. So let's look at number 4, example 4, and see how this goes. Determine whether the series is convergent or divergent. If it's convergent, find its sum. Okay, so what we have to do here is first let's try taking the limit and see if that tells us anything. So let's take the limit. This is a sub n. So this says right here, test for divergence. We can try that out. Let's take, this is a sub n. So in this case, this is our a sub n. So let's try taking the limit as n approaches infinity of all of this stuff. N squared over 5, n plus 7, n plus 1. All right, well, just so I can see this more clearly, I'm going to multiply those together. So this is the limit as n goes to infinity of n squared over 5 times n squared plus 8n plus 7. This is the limit as n goes to infinity of n squared. If I distribute the 5n squared plus 40n plus 35. That's what that looks like. We can use L'Hopital's rule. This is going to be infinity over infinity if we want to. And say, okay, well, this is equal to the limit as n goes to infinity of 2n over 10n plus 40. And we still get an infinity over infinity, so we can apply L'Hopital's rules again. And we can say the derivative of the numerator is 2, and the derivative of the denominator is 10, and so this limit is 1/5. What did that tell us? Well, all that told us was that the limit, as n goes to infinity of a sub n, does not equal to 0, so we can conclude that this series diverges. That's what we can tell. There are other methods when we're taking a limit of a quotient. Sometimes it's easy to divide both the numerator and the denominator by the highest power of n in this case. And so that would also give you 1/5. But L'Hopital's rules can certainly be applied here. All right, example 5. No, we're not to example 5. This is just something we want to look at. This is really important. Let's consider this series. This is the Harmonic Series. It has a name. It's that important. And so let's consider this. Let's try the same thing we did before. Let's take the limit as n goes to infinity of a sub n, 1 over n. And so this is 1 over infinity. We can see that this equals to 0. Okay. Unlike the last example where we could jump to a conclusion, we cannot conclude anything here. We cannot conclude anything here at this point. From this information, we have to look deeper. So let's look deeper at this one. It's an important series, so let's see what we can figure out. Let's write out a few terms. 1 over 1, okay. Let's write out like a partial sum. Plus 1 over 2, plus 1 over 3, plus 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8, 1 over 9, and some more terms. 1 over 16, 1 over 17, 1 over 18, and some more terms, 1 over 31, 1 over 32, 1 over 33, and some more terms, and keeps going. Okay, let's see, what do we have here? Well, we have a 1 here. All right, this is a 1, and we have a 1/2 here, 1 and a 1/2 here. All right, let's look at these next two terms. This is 1/4, right? And 1/3 is less than, not less than, 1/3 is going to be greater this is greater than 1/4, because this is a smaller number that we're dividing by. So 1/3 is bigger than 1/4. So if I add these next two terms, 1/4 by something bigger than 1/4, this is going to be bigger than 2/4, which is greater than 1/2. That's what those two give me, something greater than 1/2. Okay, now let's look at the next few terms. Let's group 1/5 through 1/7. Okay, let's think about this. This is 1/8, but 1/7 is greater than 1/8, and this is greater than 1/8, and this is greater than 1/8. So if I have something greater than 1/8 plus something greater than 1/8 plus something greater than 1/8 plus 1/8, all of that together, 1 plus 1 plus 1 plus 1, will be greater than 4/8, which is greater than 1/2. I'll say greater than 4/8 or greater than 1/2, all of these terms together. All right. Well, what if we say, let's take this next set. Let's see, what about 1/9 through 1/15? Okay, 1/15 is less than 1/16. I mean, sorry, not less than, I meant greater than. This is obviously greater than 1/16. And 1/14 is also greater than 1/16, all the way down to 1/9. You'll find that if you add up all the number of these, this is going to be 7 terms, plus this one would be 8 terms over 16. All of these together is going to be greater than, it's going to be greater than 8/16, which is greater than 1/2. So we're adding another 1/2 here. You can see that you can group this through 1/31, and you'll find something greater than 1/2. And you can group, and if you add this 1/32, and then you can group the next one through 1/64, greater than 1/2. So we are adding significant amounts as we go, meaning that this series will not eventually peter out into one number. It's going to keep getting bigger as it goes. It is divergent. So the big deal here that you need to recognize is that this series that looks like this is called the harmonic series, and it is divergent. That's a big deal. All right, let's look at the next example. Determine whether the series is convergent or divergent. If it's convergent, find its sum. Okay, so here we go. This is the sum of two things, and we are allowed to split these into this one plus this one. All right. Let's look here. This right here is 3/n. I can write this as, I can look at this as the sum as n is 1 to infinity of 3 times 1/n. And I recognize this as being the harmonic series. I can move this 3 on the outside if I want to. That's okay, because it didn't have an n in it. So it's 3 times the harmonic series. I can stop right there and say this is going to be divergent, because if any part of this is diverges, the whole series will diverge. So this is divergent. We didn't have to know anything about this. But, however, if you did look at this right here, either one of these would say this thing was divergent. 4 to the n, this is a geometric series where the common ratio was 4 and its absolute value is greater than 1. So this part is also divergent. But we didn't even have to have that to qualify this as being divergent. Any one part of this would make it that way. All right, let's look at part B. If we consider the sum from n is 1 to infinity of 3/2 to the n minus 1, this is the same thing as 3/2 to the n times 2 to the negative 1. All right? Plus, we can again separate these. N is 1 to infinity of 1/4 to the n, 4 to the negative 1. All right? This can be written, n is 1 to infinity. This 2, if we move it upstairs, it becomes 3 times 2 to the 1/2 to the n. If we move the 4 to the negative 1 upstairs, it becomes 4 to the positive 1/4 to the n. Then we can recognize this as the sum from n is 1 to infinity of 6/2 to the n, plus n is 1 to infinity of 4/4 to the n. This, we can take the 6 and put it out in front. Of 1/2 to the n can be thought of as 1/2 to the n. This is a geometric series with a common ratio of 1/2. Whose common ratio is less than 1? Whose absolute value is less than 1? So this has a sum. This will converge. What about this part? We can pull the 4 out in front. This becomes 1 over 4 to the n, or 1 over 4 to the n. Another geometric series whose common ratio is 1/4, whose absolute value is less than 1. So this part will converge. Question is, what do they converge to? All right. So this, I'm going to use part of my paper down here, or up here. I'm going to move up. I'm going to do it in this part. Okay. So this is going to be 6 times the sum of the series. If n is 1, that's the first term. That's going to be 1/2 over 1 minus 1/2 plus 4 times, n is 1, 1/4 over 1 minus the common ratio 1/4. Now what would have happened if I left the 6 in there right here, or the 4 on this side? Nothing. We would just have, it would still just be multiplied. It's going to turn out the same either way that you think of that. 6 times 1/2 to the n, 4 times 1/4 to the n, it will turn out the same. All right, so what we have here is 6 times 1/2, which is a 3 over 1/2. So 3 over 1 times 2 over 1. This part converges to 6 right here, all right? And then this part, we have 4. I'm going to add it to whatever I get here. 4, and then we have 1/4 over 1 minus 1/4 is 3/4. So we have 4 times 1/4 is a 1 over 3/4, or times 4/3. Okay, so we get, is that right? 1 over 3/4. So I get 6 plus 4/3 is what this one's going to add to. I got something different a minute ago. Let me just check on that one. No, I got the same thing a minute ago. What did I get there? Yeah, I got 22 over 3 is what I got a minute ago. So let's see if I get the 22 over 3. If I get a common denominator of 3, that turns into 18, 19, 22, 1, 2, 2. Yeah, 22 over 3 is what this guy converges to. All right, that's good. All right, last one. Let's consider this. Determine whether the series is convergent, divergent. If it's convergent, find its sum. We can take, consider the limit as n goes to infinity of a sub n and see what happens. So let's look at that. Of the natural log of n over n plus 1. All right, so we can rewrite this using logarithmic rules. The quotient rule gives us the limit as n goes to infinity of the natural log of n minus the natural log of n plus 1. All right, this is what we're looking at. All right, let's lay out a few terms and see what's happening with this guy. So if we lay out a few terms, the first term, where n is 1, is going to be the natural log of 1 minus the natural log of 1 plus 1, which is 2. Plus, the second term will be the natural log of 2 minus the natural log of 2 plus 1, which is 3. Plus, the natural log of 3 minus the natural log of 3 plus 1, which is 4. Plus, the natural log of 4 minus the natural log of 4 plus 1, which is 5, and so on. Natural log of, well, I get down here to n minus 1. Let's look at the n minus 1 term. N minus 1 plus n, let's see. Oh, wait, natural log of n minus 1 plus the natural log of n, or minus the natural log of n. And the last term will be plus the natural log of n minus the natural log of n plus 1. All right, lay out all these terms. Okay, what we see here is that negative natural log of 2 plus natural log of 2. Natural log of 3 minus natural log of 3. Natural log of 4 minus natural log of 4. Natural log of 5 minus natural log of 5. We're going to see all these canceling out right here. We see it here. This got canceled from the previous. Negative natural log of n plus natural log of n until we get to the very last term. So basically, we're looking at the limit as n goes to infinity of the natural log of 1 minus the natural log of n plus 1. right, what just happened here where these terms cancel each other out like that in the inner part is called telescoping. That's what that is called. But if we take this limit, the natural log of 1 is 0. We know this is a 0, okay? Then we're looking at this. 0 minus the natural log of n plus 1. So we can take the limit as n goes to infinity of the natural log of n plus 1. Well, this is going to go to infinity. So we're looking at basically negative infinity. So this is not 0, and this is divergent. So this is going to diverge, and we can say that by taking the limit. All right, and that is series.